All right, good afternoon, everybody, and welcome to Intro to Space Navigation Spring 2025. And this is lecture number 23. And let's see, should be sharing my screen now. I want to quickly revisit the course map because we're pretty close to done with the semester. For those of you that are keeping count, we only have 4 lectures left, including this one. And we've covered a lot this semester. This has been pretty dense. I think we have more lectures in this class than a normal class because there's no exam, so we have more time to cover new content. But we started off with a review of orbital mechanics. We talked for a while about estimation theory, so like least squares and covariance and all that stuff. And then we had, I believe, 2 lectures on triangulation and trilateration to include GPS and the Deep Space Network. We had 1 lecture on inertial navigation, so how to use accelerometers and gyros to navigate. Then we had a 4-lecture series on star trackers, which the star tracker homework is due tomorrow. And then we have a 3-lecture series on Kalman filters. Kalman filter homework will be posted on Saturday for y'all to get started on. And then the last unit is kind of the green one here, which is optical navigation, sometimes abbreviated as just OpNav. And so this is distinct from star trackers in that star trackers are trying to find the orientation or the attitude of the vehicle. OpNav is trying to find the position of the vehicle and sometimes the velocity. It's interesting what you can get out of images, but there's variations on OpNav, and we'll get to all of those. If you're really, really low over the surface of another celestial body, then you might be looking at individual features. Maybe you're trying to recognize craters on the moon or recognize land masses on the Earth. Or maybe you're tracking features between images. You can do what's called visual odometry. We have a lecture on that coming up. Or if you are insanely far away from planets, then actually we're back to that triangulation technique that we talked about several lectures ago, where it's like, well, this dot at infinity is Jupiter, and that dot at infinity is Mars, and I can look up their ephemeris locations. That's another technique of optical navigation. What we're going to focus on today is what's called horizon-based optical navigation. And so this has flight heritage. This algorithm flew on Artemis 1, but it is still generally pretty new. So horizon-based OpNav is not nearly as established, for example, as like star trackers or some of the other nav techniques that are, several decades old. OpNav is newer than that. And yeah, that's going to be our focus for today. So let's get started. Get my notes together. So today is horizon-based optical navigation. And I'll tell you what I mean by horizon-based in a second. And this is part 1. This should be a shorter lecture. Generally, I try to go through about 6 pages worth of notes in a lecture. That's kind of my rule of thumb. Today, there are 8 pages worth of notes for 2 lectures, which means that we're going to have 2 pretty short lectures, which is nice. Let's see. So, I'm just going to skip ahead. I'm looking at my notes, and a lot of it is the introductory stuff that I just spoke about. So here is how we're going to start. Let's say that you get an image that looks like this, where this part is dark. And then so is the rest of the image, right? It's a black image except for the moon, and then maybe you get some craters on there too, right? There you go. All right, so here's the punchline. You can navigate using this image. So I'll say, suppose you capture this image of the moon. This is enough to navigate. So bonus points. Who can tell me how? what information can we get out of this image?
Well, don't you have like the time the image was taken, and then you also have like you can identify the craters based off of like when the image was taken and the size of the craters?
So craters are good, but I want to move away from that because I have a whole lecture coming up on crater identification and crater-based navigation. So let's ignore these for a minute. But I like everything else you said. What could we do with this image?
Well, assuming you know the specifications of your camera, you know the size of the moon, you can at
Mhm.
least presumably develop a how far am I from the moon given how big the moon is in the sky or in my camera frame.
What do you mean at least? Like what else? What are you leaving out?
Um, in terms of, I mean, again, orientation, as people, as you said, ignore that for the time being.
Oh, but we can
Um,
get orientation from this image, can't we?
oh right, something star trackers. Still working on
Yeah, I
mine,
mean,
obviously.
yeah,
Um,
let's assume that you have a star tracker. Actually, there's a technique which we use in OpNav, which I could talk about later, where you could use the same camera for OpNav and star trackers, but we'll leave that aside for now. Let's assume you know your orientation, and you said you can get range from the size of the moon in the image, but then you still need the direction to the moon, right? What we call range and bearing.
I mean, you pretty much know when the moon is where the moon is relative to the Earth pretty much at all times, so you can
Mhm.
figure out like what part of the moon you're facing, like how much percent of the front side of the moon you're viewing, based on like the darkness, based on like what phase of the moon it is, I guess.
Yeah, you can look up phase angle. I think y'all are actually overthinking it. It's even simpler than you think. When we do the image processing, what we do is we just scan from the edge of the image until we hit a horizon line. And then we do this several times. And I'm assuming that you know your illumination direction. So these scan lines are actually based on your illumination direction. So these will be parallel lines. And we'll catch one more right here. And then from here, you just fit an ellipse to these red points here. So even though in the image you'll only have these lit pixels, these will be black, right? You can fit an ellipse, you can recover, well, let's try a little harder. You can recover the original circle, or in general, it's an ellipse. And then the center of that is the direction. So you just, the pixel coordinate of the center of your ellipse is your direction. And then the width of the ellipse is your distance. And now you have range and bearing in the camera frame. And then you would need to be able to go camera to inertial, which is the whole star tracker problem, to be able to take it from there. So you could do this also with a star tracker. So assuming you have like a star tracker and an OpNav camera, that's a perfectly valid way of doing things. You'll need to know the angle between the star tracker and the OpNav camera, but you can calibrate that. Or you could say, and this is where it gets tricky. This is we're kind of freestyling here because this is not in the lecture notes, but in case you're curious, because this does come up for like Artemis stuff. You can't get stars and the planet to look good in the same image because of exposure, right? The stars are very, very dim, whereas the planet's very, very bright. So if you change your exposure settings for Earth or Moon to look good, then you will have no stars in the image. They'll be completely black. And if you turn up your exposure so that the stars look good, the moon or the Earth will be not just like saturated, but completely blown out. What's called blooming overexposure effects. It's unusable, right? And so the idea is, what if we take several images, what we call bracketed images, where we do a star exposure image, followed by an Earth exposure image, followed by another star exposure image. You can run the first image through your star tracker algorithm, and then get your attitude of your camera, and then run the next one through your OpNav algorithm to get your position. And now you don't need a second instrument. You can do it all with one camera, that sort of thing. So that's kind of the nominal ConOps. But anyway, so we're kind of going off the rails here, but I wanted to just make sure people knew the gist of what we're talking about here. Now, the way we explained it, we might have oversimplified it a little bit. It's a little bit more complicated than that. We're going to talk about the theory behind finding your position with respect to this celestial body. And it's a bit more than just the width of the thing in the image, but I'm glad that we get the big idea just from this, like, high level discussion. So processing an image of a planet or moon to find its horizon line and estimating relative pose is referred to as horizon-based optical navigation. Or OpNav. Okay, so to start, I think it was Peter that gave the quick synopsis of how we would process this image, and if it was, great job. Good credit to you. We need to know, you mentioned this in your description, we need to know the shape and size of the overall body that we're working with, be it the Earth or the Moon, or this same technique will work for planets of Jupiter and Saturn, same idea, right? But first, we need to be able to describe the global shape of a large celestial body. So first, is Earth a sphere? I think most folks know the answer to that is no. It is what's called an oblate spheroid. So that's to say that the Earth is wider at the equator than it is tall, right? And not by a huge amount, but by a considerable amount, enough that we would need to take that into account. Here's another question. Is the Moon a sphere? And the answer to this one is kinda, yeah. It's pretty close to a sphere. It's close enough that you can treat it as a sphere for most navigation purposes. Right? So planets and dwarf planets and moons are often well modeled as triaxial ellipsoids. And a triaxial ellipsoid is going to look familiar because it's the same shape as a 3D covariance. So you're going to get kind of like this football shape with some cross section here, and then maybe some other cross section here. I'm going to try that again. There you go. Hopefully you get the idea. And the way this is drawn, we'll say that it has some semi-axis A, and then some other, I guess if this is the center, then maybe I should draw this with, let me try a little harder with the perspective here. So from the center out to here, that distance is A. And then from the center up to here, that distance is, we'll say think I have that as C. And then this distance is B. Doesn't really matter. The point is you've got a length, a width, and a height, or kind of a half length, half width, half height of this triaxial ellipsoid, A, B, and C. And the equation to describe this is x squared over A squared plus y squared over B squared plus z squared over C squared is equal to 1. So a point xyz lies on the surface of this ellipsoid if this equation is true. Okay. And I should be clear, this is true in the principal axis frame. Right, so we're assuming x is some direction this way, y, and then c, that sort of thing. This is true in the principal axis frame. Okay. So some common triaxial ellipsoids. We've got if A and B and C are the same, that is a sphere. If A and B are the same and then C is smaller, this is an oblate spheroid like the Earth. Right. And then if A is the largest and then B and then C, this is the general case. Now, you might be saying, what about Phobos and Deimos, the moons of Mars? They're not triaxial ellipsoids. Or what about Bennu, the asteroid? Maybe you've seen some photos of Bennu taken from OSIRIS-REx. That's a weird shape. That's like a kind of potato shape. It's not a nice, clean triaxial ellipsoid. Can we use OpNav for those? And the answer is no, not the techniques that we're going to go over today. Today's techniques, it needs to be a sphere or pretty darn close. Now, there are some really nifty optical navigation techniques, especially the OSIRIS-REx folks published some really cool stuff about Bennu. I would encourage you to go look into that. Maybe if you're still shopping around for a project idea, take a look at OSIRIS-REx. Some cool OpNav techniques for that. But in this class, for today and the next lecture, we're going to be talking about the Earth, the Moon, or like Mars, or like Ganymede and Callisto, some of the larger moons of the outer planets. That's kind of the idea here. So let's say, let the point P, it's time for math. Let the point P be lying somewhere on the ellipsoid surface. Well, we can take this equation, which is a scalar equation, and rewrite it as this. Let's say that P in the principal axis frame is X and Y and Z. And let's say that some matrix A in the principal axis frame is 1 over A squared, 1 over B squared, 1 over C squared, zeros on the off diagonal. Then we'll say that P transpose A P is equal to 1. Okay. So this is just the same exact equation that we had above, but now we've put it into matrix form. What's cool about this is that this is true in other frames as well. So you could describe P, the vector, in a different frame, and as long as you also take pains to describe A in that different frame, this equation still holds. So later we'll talk about how to take this matrix and put it in other frames. But for now, before we move on, we're going to give it a name. AP is the planet shape matrix. Okay, questions so far? Oh, sorry. I thought I was at the end of this part of the notes, but there's more to say. Let's see. clear about this too. This is the principal axis frame. And we'll say that since AP is diagonal, it can easily be inverted. So AP inverse should come as no surprise. It's just A squared, B squared, C squared, zeros on the off diagonal. Okay. Now, what if we wanted to express the celestial body's shape in a different frame? Okay, so let's say that P in the principal axis frame is P in some other frame, like maybe the camera frame. Well, what's the relationship between these? Well, it's going to have to be T, C to P, right? Camera frame to principal axis frame. So we're not talking about where we get this from yet, but for now, there is a matrix that describes the relationship between these two frames. And so what we can actually do is we can say that P transpose AP PP is equal to PC transpose T principal to camera, AP T camera to principal, PC, right? All we did is make this substitution, TCP PC in for PP in the previous equation, and you get this, where we can say, this right here is just a C. Okay, and now we've got PC transpose AC, PC, which is still equal to 1. So this is what I alluded to before. You can express the planet shape matrix in the camera frame simply by using the direction cosine matrix from camera frame to planet frame, but you'll need to kind of sandwich it on either side, the way we usually do when you're trying to move a matrix from one frame to another. You've got to sandwich it. Okay? And so this is the planet shape matrix in the camera frame. Okay. So let's see. Next is rotation and translation problem setup. So suppose we want to consider a rotation and a translation. Oh, got ahead of myself. A rotation and a translation with respect to the principal frame. So we're going to make some definitions here. We'll start with a circle. And say that the center's right there. And let's say that there's some point on the edge of the planet. And let's put that point right there and say that that is point P. Okay. So really, let me zoom all the way up to the top for a second. When we're taking an image of the Earth or the Moon and we're finding the horizon, and then we're processing that horizon, we're basically getting points which are on the surface of a triaxial ellipsoid. So P is what we are measuring, or not necessarily directly. It's more like the vector from the camera to P in the camera frame, right? So let's put a camera out here. I'm going to draw like a video camera, right? And let's say that it is measuring some vector here. Then also you've got this. Okay. So as drawn, R is the position of the planet with respect to the camera, not the camera with respect to the planet. So you'll have to put a negative sign on this if you're solving for the spacecraft position, but one thing at a time. We're going to call this vector from the camera to a point on the surface of the planet, zeta. And this is how I draw my zeta. So as drawn, zeta, you can use a different letter if you want to, is R plus P. Or you could say that P is zeta minus R. Okay. P in the planet frame is T camera to planet. Zeta in the camera frame. Remember, zeta is basically what we're measuring, right? What we're going to hit in the direction of, at least, is a unit vector from the camera to a point on the surface of the planet, right? So zeta is what we're measuring. And then this would be minus position in the planet frame. Or you could just say that this is zeta P minus R P. Okay? We can account for rotation and translation simultaneously using homogeneous coordinates. Okay. So this is where, again, we are going to introduce a new notation. And sorry about that. This is going to be a little bit confusing. We're going to say that P hat, the hat is not a unit vector in this lecture. Just want to be clear. Not a unit vector. This is going to be its original self, TP, with a 1 appended on the end. And then similarly, zeta camera hat is zeta camera the vector and then a 1 on the end. So this is going to be a 4 by 1. 4 by 1, 4 by 1. So then our equation is that P is related to zeta C, and we could do the rotation and the translation all in one shot and just say it is T C to P negative R P 0 0 0 1. So this is going to be a 4 by 4 homogeneous matrix, which contains a rotation and a translation together. And if this seems a little bit weird, you can just go through and write it out, and you'll see that all we're doing is expressing this equation as one matrix relationship by basically putting things up in the 4th dimension by adding this extra 1 here. Makes things nice and simple. Okay, so again, we haven't quite gotten to where we're going yet, but hopefully it makes sense that we are building in the direction of being able to put together an equation. What we're really after is a simple equation. Well, maybe simple might be asking too much. We're looking for an equation that relates our position, the camera's position with respect to the planet, R, to these things that we can measure, zeta. But there's some extra steps, and we'll say, well, one thing at a time. Do we, look at my notes here. Okay. The next bit is called the quadric locus. Okay. So we'll say, recall from just a minute ago, this P P transpose AP PP is equal to 1. Or you could just as easily say PP transpose AP PP minus 1 equals 0. That's fine. So you could write this in matrix form and say PP hat transpose, and then we've got AP, which is the 3 by 3, 0, 0, 0, 0, 0, 0, negative 1, and then P hat equals 0. So all we're doing is we're using the homogeneous matrix from before. This guy is now no longer AP. It's like AP with zeros and a negative 1. We're going to call this QP. Okay. So if QP, the matrix, is full rank, which would need to be a rank of 4, it describes what is called a proper quadric locus. So this is the set of all points lying on a non-degenerate quadric surface. So that would be like a sphere or an ellipsoid. So to clarify, in this case, degenerate does not mean makes questionable life choices. Degenerate means like some kind of broken or warped version of the original thing. So like a degenerate sphere would be a disk, right? Like something went wrong and that sphere lost all size along one direction and now it's a disk. That's a degenerate sphere. So we're not talking about those. We're talking about spheres and ellipsoids. And so this QP is the matrix which describes this triaxial ellipsoid in 3D space. And let's see. You might see where we're going with this. Here we have some 4x4 matrix math. Here we have some 4x4 matrix math. They both involve this PP. So maybe you can see where we're going with this. If PP is this matrix times zeta C, then we can substitute. So next, we substitute. Where zeta C transpose, okay, and then we've got T to C. So what I'm describing here is the transpose of this matrix up here, right? TP to C, 0, 0, 0, 1, and then we have negative RP transpose. Okay, that's a matrix. And then we have AP, 0, 0, 0, 0, 0, 0, negative 1. And then we have the regular form, which is T, C to P, and then negative R, P, 0, 0, 0, 1, and then zeta C is equal to 0. Okay, this is a bit much. Thankfully, this simplifies. To, well, maybe not. It's actually going to get a little ugly, but bear with me. It's going to get nicer in the end. So we have zeta C transpose, and then this whole thing is going to be what? It's going to be T, P to C, AP, T, C to P. And then it's going to be negative T, P to C, AP, RP. And then we've got negative RP transpose, AP transpose, but it's a diagonal matrix, so transpose doesn't do anything. and then T, C to P. And then finally, we get RP transpose AP RP minus 1. And then all of this times zeta C equals 0. So all we did was take those three matrices and combine them analytically. But this simplifies even further to zeta C transpose, get what? I'm going to call this AC, because remember we said you can take a planet shape matrix, and if you sandwich it between direction cosine matrices, you end up with that planet shape matrix in a different frame, call it AC. Well, let's play that same game. This should be negative RC, sorry, negative ACRC. And then this would be negative RC transpose AC. Well, transpose, but doesn't make a difference. And then finally, we get RC transpose ACRC minus 1. And zeta C is equal to 0. Okay. Where this, I mean, all we've basically done is take the quadric locus matrix QP, and we've involved a rotation and a translation, but it's still the same shape, it's still the same sphere or ellipsoid underneath. So this is actually still Q. This is just Q that we've taken pains to put in the camera frame. Okay, so now we have this zeta transpose Q camera zeta equals 0. Right? So now I'll say where QC is a 4 by 4 symmetric matrix describing the proper quadric locus in the camera frame. See, this QC 4 by 4, it has the shape of the original body and the rotation and the translation all baked in. Okay, so just want to be clear that we've made some decent progress. We're still not quite there yet, but just an understanding checkpoint. This matrix, which we're still making friends with, QC, sandwiched on either side by some vector, which is zeta C, but we said zeta is the vector from the camera to a point on the rim of the planet. Okay, so zeta, it's not quite something that we measure because we don't measure zeta directly. We measure a unit vector, zeta, but we're making some progress. We're saying that zeta times this matrix we don't understand times zeta equals 0. Okay, so you can see how we're building in the direction if we know the translation and if we know the rotate, well, sorry, if you know the rotation and you know the shape matrix, we should be able to back out the translation RC. So that's kind of where we're going. Just want to make sure that nobody's feeling lost. So quick knowledge checkpoints. Anybody feel lost or are we doing okay so far? Okay. Believe it or not, there's just one more page of notes. So I think we'll actually finish in under an hour today, which is good because that'll give us loads of time to talk about homework 4 after class. Okay. So the next thing I want to discuss is a celestial body's what's called a tightly bounding cone. So remember, every point in an image corresponds to a direction in 3D space. And a direction can be expressed as a unit vector. Okay. So the horizon points in an image become unit vectors tangent to a triaxial ellipsoid. So you can think of it this way. Let me start with a planet. And I might also do a I'm gonna do it this. Hang on, bear with me. Oh, I want to get my. I'll just draw this one. Sorry. I wanted to do like kind of a trapezoid to show the perspective here. And then imagine we have a camera that's right here. Okay. So this is where I might do, let's see, automatic shapes. Is that going to work? Yes. Okay, cool. Technically cheating, but that's fine. Good. I might actually try this first one again too here. Nice. Okay, so let me turn off automatic shapes. So let's see. Also do, this is fine. Okay. So this right here is the edge of the planet in the image. And you're going to get points right here, which are going to be points on the edge of the planet. Just like so. And then similarly in your image, ooh, you know what? Now I'm spoiled by the automatic circle. Let me try a little harder here. Maybe I'll make it a bit of an ellipse. Is that gonna work? Yeah, that'll do right there. There you go. In the image, you're going to get a flat circle with points on the edge. Really, we know these are tangent lines to a sphere or a triaxial ellipsoid in 3D space. So in here, you get an image conic. This is our triaxial ellipsoid. And then this bit, imagine that this is kind of like a like the wrapper around a bouquet of flowers, right? That sort of thing. You get this kind of conic cone shape that tightly bounds the planet. Aha, that's the name. It's the tightly bounding cone. Okay. So these 3D directions, so the pixel image points, form a tightly bounding cone. And I realize that my text is a little too close to the diagram here. I'm just going to scoot this down. tightly bounding cone, and we're going to use the letter chi, the Greek letter chi for this, which just looks like curvy X, with apex a hat. So apex would be the point of the camera, essentially, right? So the way we're going to put this is chi is proportional to, right? Because this cone goes on forever. So equal signs are tough here, but it's going to be proportional to Q apex, Q apex transpose, minus apex transpose Q apex, which is a scalar, times Q, where chi is a 4x4 symmetric matrix of rank 3. Okay. And we can say, so this is just how to build chi. So chi is this 4x4 matrix, rank 3, that is built from Q and apex A. Okay. So while I'm throwing things at you with no derivation here, a direction zeta lies on the cone if zeta transpose pi zeta equals 0. Okay. So if we have a camera and an ellipsoid in the frame, or we'll say in the camera frame, then the apex is just going to be all zeros, right? The camera is 0 in its own frame. The 1 is because we're in homogeneous coordinates, right? So it's 0x, 0y, 0c, and then 1 in this kind of fourth dimension that we're bringing along with us. But don't get too hung up on that for now. QC is going to be AC, negative AC, RC, negative RC transpose AC, and then RC transpose AC, RC minus 1. Okay. Now we're trying to build chi. So one of our steps is we're going to need QA. So QCA hat is just going to work out to be negative AC, RC. It's going to be a 4x1. And then RC transpose AC, RC minus 1. And then finally, A transpose QA, QCA, hopefully isn't too surprising. It's just going to be RC transpose AC, RC minus 1. Okay, so we're building towards something, and bear with me here. We said that chi, this tightly bounding cone here, chi is going to give us, it's going to be QA transpose minus AQA times Q. So we need to actually go work that all out. We're only going to have to do it once, though. We're going to say chi is proportional to, here it comes, ACRC, ACRC transpose, negative ACRC, RC transpose AC, RC minus 1. And then we've got RC transpose AC, RC minus 1. And then negative AC, RC transpose. And then RC transpose AC RC minus 1 squared minus RC transpose AC RC minus 1 multiplied by AC, negative AC RC, negative RC transpose AC, and then finally RC transpose AC RC minus 1. Okay. So hopefully we see all we did was we just plugged in A and Q into this equation above, and that gives us this tightly bounding cone, okay, where we have direction transpose chi direction equals 0. And so after we simplify this, we get that chi is proportional to, thankfully this simplifies quite a bit, AC, RC, RC transpose AC minus RC transpose AC RC minus 1 times AC. So all of this is going to be a 3 by 3. And then it's just zeros everywhere else to create our 4 by 4, where we will define this top left bit as just MC, 0, 0, 0, 0, 0, 0, 0. That is our matrix. Okay, so chi is our 4 by 4 matrix of rank 3, which describes this equation of the tightly bounding cone, which allows us to say that zeta transpose chi zeta equals 0. Great. So we're not there yet, and unfortunately, we're not really going to get to a very satisfying point in this lecture. I got to kind of leave you on a cliffhanger. Where we're going next is how to go through and take this the rest of the way to an equation where we can solve for RC. And let's see, into my notes. Yeah, that's about it. So we're about halfway done with the OpNav lecture. We're going to kind of stop on a cliffhanger. We'll say until next time. And by the end of next lecture, you'll have everything that you need for homework 6, which I promise is not as bad as homework 4. Right? Homework 6 is going to be one of the easier ones, actually. But anyway, any OpNav questions, or can we stop here for the day and then switch to office hours? All right, cool stuff. So thanks, everybody. I'll stop sharing and stop recording. If you're done with homework 4, then class is dismissed. But if you'd like some help, feel free to stick around.